You're live, it says. I'm live. Howdy, howdy. We're getting started soon here. There we go. Stream will begin soon. Submit your math questions. Thecalculustutor.com. All right. Cool. Well, I'm going to go grab my coffee. I feel like there's something else I wanted to do real quick, too. Maybe I'll remember. Either way, go grab my coffee. Give you all a chance to submit questions. I'll come back. For those of you that aren't sure how to submit questions, we'll go through it when I begin the stream, which will be anytime now. Howdy, howdy, I'm back. So, I am here to answer your math questions. My name's Ryan. I'm the calculus tutor. I'm here to answer your math questions. I assume from school, but your math questions from life. Or just anything you think you would like to be able to take sort of a mathematical look at. I want to help make math a useful tool for everyone. That's what it is. It's a useful problem-solving tool. It's my favorite problem-solving tool. We can get rid of this before the stream begins now. If you would like to submit a question and have me answer it here live for you, what you can do is you can go to thecalculustutor.com. Thecalculustutor.com. This is what you'll see. Oh, well, hold on a sec. Oh my God, I forgot. My site's just a tad bit busted right now. It's just a small thing. I have to go in and manually get this. Oh, there we go. Okay, there we go. So now, if I do that, haha, there we go. Try it again. Headband already coming off. That's fine. I'll fix it in a second. All right. So if you go to calculustutor.com, this is what you should see. You can click right here in the pink streaming box. You can click the submit a question. That'll take you over here to the streaming page. It'll scroll on down to the submit homework problem section. And as you can see, there's a homework submission form button right here. Or email your questions to Ryan at thecalculustutor.com. And here are some guidelines if you're going to email me the questions, right? Let's look at the form. So if you click on that button, what will probably happen is it'll probably ask you to sign into a Google account if you're not already. That's because you can submit files, images specifically on this form, so you can submit pictures of your questions. And if you do that, Google requires that people who submit the form be signed into a Google account. So you have to be signed into a Google account. So go ahead and do that. If you try to use your school Google account and then it tells you can't access the form, I apologize. Feel free to email me your question, or you can log out of that account and log in with, say, a personal Google account if you have one and you want to use it. If you do email me though, or have to log in with with a personal account or whatever, feel free to include somewhere in here. Hey, I tried to log in. I tried to use your form with my school account and it wouldn't let me. If you tell me what district you're with, I will reach out to them and see if there's any way I can make it so you can access it. Anyway, all of that aside, before you see the form, it might ask you to sign into a Google account. Go ahead and do that. And then it should take you here. And if it doesn't, feel free to email your question to Ryan at thecalculustutor.com. But I assume it will. You have to check this box to say, yes, this is my email address, include it. Tell me who you are. This doesn't have to be your real or legal name. This is just how you want me to refer to you. So if you have a preferred name, if you have a username or a screen name you want to use here, that's totally fine. This is also where you could include your pronouns if you care. Otherwise, I'll probably just use they. But this is mostly so I can be like, this question was submitted by such and such. and you can listen for when I'm answering your question specifically. Um, so that's just really how you would prefer for me to refer to you when I'm answering your question, including pronouns if you care. Where did this question come from? That's the teacher in class, because I assume most of the questions I'm going to get through here are from students for homework or test prep or whatever. So that should be really simple, just like Mrs. Jacobson's geostats. That's all you need. If it's not from a class, if it's just from your life, mention that. Give me a little, just a few words to say how you came upon this problem, how this problem came into your life. And then the main section here is, what is your question? Um, so be as specific as possible here. It, uh, so when you're doing this, be aware you don't need to like copy, like retype the entire math question into this box, because at the bottom, the last thing you'll do is you'll attach images. So my hope is you'll just be able to take a picture of the problem and attach it. So in that case, what do you put here? Well, if your picture is like the whole, worksheet, or uh, a picture of just like your whole textbook page, or you submit the entire PDF packet that you got from Canvas or whatever. Uh, this is where you direct me to where to go. So even if you took a zoomed in picture of just your problem, uh, it would still be useful for you to put something here. Uh, so you could say something like, uh, you know, number 13. Um, I don't know how to factor when there is a number in front. There we go. Something like that, right? Um, Boom, one sentence. Uh, you know, I didn't even put any punctuation in. This isn't English, and the purpose of this is not to be a barrier. It's for you to help direct me to the real part of the problem that you're struggling with, right? And now sometimes you just want to have me work through the problem so you can sort of follow along and see what it is, and that's totally fine. Or you're not sure where to start, you can totally tell me something like, these aren't like the problems we did in class, right? That doesn't tell me anything about the specific problem necessarily, but it does tell me you're not recognizing it, right? And so that tells me to maybe start from the beginning, maybe even go back a little ways and sort of connect this problem to sort of what might be previous content. Um, I would recommend, if this is sort of if say your question is something like this, like, oh, we were asked to do these problems and we didn't get we didn't get shown how to do them. Send me a picture of the problems you did do in class, right? So I can see, are they similar at all, or I can confirm for you you're not crazy. These are nothing like the problems you did in class. They're a totally different thing. They're unrelated, um, right? And confirming that for you could could be a relief. You're like, okay, I'm not going crazy. I'm not so bad at this that I can't even recognize it. So yeah, use this in whatever way is most useful for you. There's a place here for you to direct me to what would be most useful for me to talk about. And then we're going to skip this section really quick. There's the place for you to submit pictures. My idea here is that you'll submit a picture of the problem or set of problems that you're working on. And then up above, you'll describe specifically where you want me to focus. When you do submit these pictures, uh, the goal is to be clear and complete. So clear means I can read it. It can be easy to take a blurry picture of text, right? So just double check the photo before you attach it to make sure it's legible. And listen, it doesn't have to be perfect. I'll do my best to parse it. And if I get something, I'm like, I can't tell if that's a 5 or an 8. Um, I'll just I'll just make a guess. Maybe you can be in chat and you can clarify for me. We can figure it out. So it doesn't have to be perfect. So that's the clear part. Complete means don't accidentally crop off part of the problem in your picture. That's easy to have happen. Um, so that's a very basic thing, but make sure the whole problem is there. But in addition to that, complete also means make sure any diagrams or charts that are part of the problem are included either in your image or take a separate image. You can attach up to 5 images to this. Take a separate picture of those things, including like if you're given a coordinate axis that you're supposed to draw a graph on or a number line that you're supposed to draw on or something like that. Send a picture of that, even though it's blank, or even if it is blank. If you send it in, I will use it in my notes to show you. So what I do here will look exactly like uh, what I assume your teacher will want you to see from you. Um, so yeah, attach those. The other thing is the instructions. Oftentimes, there's like a separate block of instructions for a group of homework problems, right? Either at the top of the worksheet or in the textbook. Here's the instructions, and then you have like a dozen problems that follow those that you're supposed to use those instructions for. So make sure your picture either includes those instructions or again take a separate picture and include that. And then finally, the other thing you might attach, and I alluded to this earlier, is you might attach any work you've done on the problem. If you tried the problem but you can't seem to get the right answer, or you're getting stuck or something like that, or you just get to a place where you started it but you got to a place where you weren't sure what to do next or you got confused, anything like that. Show me the work you have done, or show me any notes that are about that type of problem that you did in class that day or recently, or if you did another problem like that elsewhere in the homework or in class. Send me any work you did like that. Any of that. You don't have to send me a ton. I'm saying send me one of those things. um, any extra little bit you send me of your own work can help me understand where you're coming from, honestly, kind of quickly. uh, and so that's what this other box up here is about. My promise to you, if you send your own work to me, that won't show up on the stream. That won't show up on the screen. That's just for me to look at and inform what I focus on when I'm answering your question, that sort of stuff. Um, so yeah, it is useful for you to send that in. I promise it won't show up on stream. The reason this box is here, the reason you could check this box if you chose to say, I could show your work on stream. You're like, who would want that? Why would they do that? For students in like pre-calc, calculus, or college or university students, the problems get complicated enough that it actually could, what they might want is for me to go through their work on the problem because it's like a lot of steps and double check their work, see if everything they did actually is correct. So, and this is the thing you can do. Say you have a review assignment for a test, but the teacher didn't provide the answers for the review assignment, which kind of makes it useless. So say something to your teacher about that. Um, or they did provide just the answers, but not like the solutions, not the correct way to get those answers. And so you want me to check through your work for like your on your test review or whatever. um Send that to me. I will check through it and I can go through it. The easiest way for me to do that though is if I can actually just take your work and go through it on stream rather than having to look at your work here and try to figure out a way to address it. You see what I mean? So that's it. That's for a very particular type of need. So there's an option here. People can check that and say, yeah, what I need you to do is show my work on screen so you can go through it and sort of show me what I did right and what I could do differently and that sort of stuff. So that option is there for people who need it, but I assume most people won't use it, and you can ignore that box. It will remain unchecked, and I will not show your work on stream. But please send it because it is helpful to answer your questions. But anyway, that's how you submit a question. Feel free to submit multiple questions. You can use one form if it's all like the same type of problem. You're like, oh, uh, we need to do all these even numbered problems, and problems 18 through 24 are all the same type of problem. um So, you could just send in, oh, I need to do 18 through 24 evens, and they're all this particular type of problem, and you include the instructions and all of that. Um, and that's totally fine. I'll choose what I think are the best, the most the toughest one or the best example ones. I'll choose those ones to do, and if we have time, I can do multiples. Um, if it's a totally different type of problem, though, send it as a separate form submission. Don't try to bundle different types of problems into a single form. It'll just confuse things. But yeah, that's the form. If you can't access it, um, you can email me, Ryan at thecalculustutor.com. Please tell me that the form wasn't working for you. Um, when you email me, because an email is just a blank canvas, right? You don't have prompts. Here are the prompts. It's just the same things that were um, in the form. How do you want me to refer to you? So just tell me your name and your pronouns if you care. Where did the problem come from? Teacher in class or where in your life the problem's coming from? Your specific question. Remember, like one sentence, one or two sentences. More if you want to, but that also then attach images or paste images into the email, screenshots or pictures from your textbook, your worksheet of the problem, and that way you don't have to. When you ask your specific question, you can then specifically say, oh, specifically in the images, this particular thing is what I was struggling with, or what I'd like you to talk about. Um, so yeah, that's the whole process. That's how you participate. The notes, I will answer questions, um, and you'll probably want to follow along, or if you want to access my the solution, my work outside of a stream, and stuff like that, or you want to zoom around, you can see right there, there is a go to notes button. There's also under the math live streams category up here. The only thing in it right now is math notes. That'll take you right to the notes document. On the home page, same thing in this pink streaming box. There's a go to notes button there. And so if you click those, what those will let you go to this notes document where I'm going to do any math work we do and put the problems that we work on and things like that. Um, and that way you can both follow along, but also, I think more importantly, not follow along and access the parts of it that you need to access. Especially like if I've moved on to the next problem and you're going back and want to look at the problem I just worked on because you submitted it or because you had the same or a similar question or something. Yeah. So you'll be able to go to this same document, zoom around. You won't be able to write anything in it, put anything in it. It's read only for visitors. Um, but you will be able to see in real time as I'm interacting with it. So, yeah, that's the process here. I guess I should check for submissions. Okay. I don't see anything in here. Excellent. So we do have some stuff to talk about. I have. So yesterday we worked on some related rates, or sorry, some optimization problems. Um, I just had a student just before the stream that I worked with on related rates, so that was still in my buffer. We were doing some optimization problems. I have one more of these problems to work on, and then With any time left, I want to talk about, um, I think, depending on how much time we have left, I'll want to talk about factoring. If I don't do it today, I might do it tomorrow, but also I need to figure out if the stream tomorrow is going to happen. There's not going to be a stream to actually. Now that I think about how my schedules has landed. Okay. So there won't be a stream tomorrow. So if I don't do anything about factoring today, if there's not time, um, then I will go over it on Sunday, on the Sunday chill stream. And honestly, that could be a great thing for a Sunday chill stream. So, with that in mind, let me go grab this last optimization problem. Okay. This is our problem here. A steel pipe is being carried down a hallway 9 feet wide. So here's 9 feet wide. At the end of the hall, there's a right angled turn into a narrower hallway 6 feet wide. This right here. What is the length of the longest pipe that can be carried horizontally around the corner? That horizontally there is doing the same thing as like basing your movie in the 90s so there can't be cell phones. Because if you can lift the pipe up, it makes solving this problem harder. We have to have more information, but it also makes solving the problem for us harder, but it makes solving the problem in real life easier. You have all of that full extra dimension to play with. But regardless, we are going to take this. It's just these two dimensions. There's no vertical dimension here coming towards us, or Z dimension coming out of the page. Use right triangles to express the total length as. Oh, that's very nice of them. Look at that. Well, this right here, this is the punchline. They just sort of gave us the punchline here. So which is nice because the setup to this problem is not calculus. The setup to this problem is geometry, which is important to have some skill with. But ultimately, this problem wants you to practice the optimization skills. So what are they getting at here? L. So they're calling. Do I have a teal that can match that? I do. They're calling this distance L. Oh, it's very vibraty, isn't it? Some of you probably hate that. Okay, so we're calling the length, this teal pipe distance. We're calling that L. So let's look at this in pieces, shall we? 9 divided by sine over theta. So what they're doing is if you draw a line right there, you can see we have a right triangle. This distance is 9, just like this distance is 9. We have an angle theta here that they've nicely given us. Um, okay. And we can set up, if we call, we're going to call this right here, we're going to call this L1. And so we can set up an equation because we have this theta. This 9 is the opposite side. This L1 is the hypotenuse. So we can say sine of theta is equal to 9 over L1, which we can rearrange this. If we do some algebra, multiply by L1, divide by sine, we can get that L1 is equal to, oh, look at that, 9 over sine theta. Oops, sine theta. Well, if I could try a theta to save my life. Okay. And there we go. There's L1. And there's that 9 over sine theta. Now, let's draw a line here. We're going to talk about 6 over cosine theta. And I think hopefully you can see where this is going. This theta here is the same as this theta here. We could go through some angle proofs. This is, again, this is geometry stuff, right? That's why them giving you this is so useful. And I could have just jumped on that and said, okay, they gave us that. I think it's important to understand where that hint came from and how useful that is, because there's a lot of problem solving that gets skipped over by just getting that single value, right? Just being able to call this whole distance a single L, even though it's sort of split into two pieces. I'm going to call this section over here, you might be surprised, but we're going to call it L2. And now we have theta which we can do some rearranging and solve for L2 and show that it's equal to 6 over cosine theta, which is exactly what we have up there. And yeah, L1 plus L2. And because these angles are the same, we know this pipe is not bent. We know L1 and L2 are parallel to each other in that they intersect each other completely. They could lie on top of each other. Okay. And now we can say, okay, L, or rather, L is equal to L1 plus L2. And therefore, yeah. So we got that. Or rather, I suppose it goes the other way. Zoop. Boom, boom. So this, oops. L equals 9 over sine theta plus 6 over cosine theta. This is our optimization equation. So here, what is the length of the longest pipe that can be carried horizontally around the corner? Yeah, so this is our This is our optimization equation. We want to find the max of first. Let's consider our practical domain of theta. That is what values of theta are relevant. Did I spell relevant wrong? I think it's A-V-A-N-T. Relevant to this actual situation. Well, theta cannot be less than 0. So, when you're dealing with problems like this, and actually, oh no, I'm not sharing my screen, y'all, or my screen share broke at some point or something. I'm so sorry. No, it says, yeah, see, this one says I am sharing my screen, but my actual view of the stream says I am not. So I do apologize. This is why going to the notes is valuable and useful. Because even if this breaks, you could still be in the notes and you can see where my cursor is in the notes, so you can see right where I am and where I'm writing, and basically follow along. But okay, so let me go back through this really quick. Let's review. So we figured out. So they gave us an equation for L, and we could have just jumped right there. But I think it's important to make sense of this, and a less kind problem would not have given that to you and just given you the problem and said, figure out how to make sense of the L value there. And this is the way we would have done it. So I wanted to make sense of that. But now we understand, okay, this L is the length of the pipe, and we understand where these pieces come from. They come from the two different sections of the hallway. We want to find the max of L, and L is this equation. So we need to find which angle we can plug in so that L is as big as possible. So since we know we're looking for that theta, let's consider the theta values that are possible. Because if we think of angles, right, you could have a negative angle. That just means rotating the opposite direction. You could have angles of thousands and thousands and thousands of degrees. That just means you've rotated multiple times, right? And so in a rotation can be a full circle, and I don't think it would make sense for theta to be 360 here. So let's figure out what values of theta do make sense, and that's going to sort of narrow in our focus. And as we go through the problem solving process, it's going to help us when we realize that we have infinite solutions. It's going to help us say, okay, yeah, but we actually only care about solutions in this little narrow domain. And that's why we taught you. That's why you were taught about domain and range for so long without ever really needing to use it for anything other than just being asked to identify it. It's because when you get to complicated problems, you need to ask yourself questions about domain. So values of theta, if we look at this diagram, theta is here. So the pipe could be totally horizontal. Or rather, the pipe could be totally parallel to this wall. That would be 0 degrees. Let's start there. And then we could bring it in, but we would only be able to move it side to side. We would never get it around the corner unless it was less than 6 feet, right? So if we had a little short pipe, that we were bringing in, right? So we bring that in. And look, keeping that horizontal, keeping that parallel to the wall, the left-hand wall, it still fits down the hallway. We can still fit it down the hallway. And the largest possible pipe would be 6 feet. Oops. But if we make it bigger than 6 feet, can I can I zoom in and make it bigger? Right now, all of a sudden it won't fit. But if we rotate it, and I'm just explaining the problem to you here now. If we rotate it, we can rotate it far enough that now it will fit down the hallway, right? And we could rotate it, but now we say, well, okay, well, let's make it so 0 degrees, the largest one was 6 feet. So the furthest we could go, if we made it parallel to this one, well, now any size pipe will fit down here. But look, we wouldn't have, if it's too big, we wouldn't be able to get it down this hallway. If it's too big, we can't get it down this hallway. So we still need to carry it at an angle down this hallway, right? So the problem here is we need to be able to get it down both hallways. But we also we can change the direction while we're in the hallway. So we start here, we're like, okay, well, we're gonna go here, we gotta turn it. Right. And so this is our issue. Um, so it can be parallel, we'll call that 0 degrees, or it can be this direction, and we'll call that 90 degrees. But then if we turn it more than that, um, well, now we're just sort of, this is the same as this for us, right? It's just facing the other direction. Does that make sense? That this position and this position are equivalent to each other. So we actually don't need to consider anything beyond 90 degrees. Because once we're at 90 degrees, now we're back to a short pipe. So somewhere in between 0 and 90 is that longest possible pipe that can fit down this hallway. Okay. Cannot be less than 0. So 180 degrees would just make it parallel to the hallway again, right? And 90 degrees, uh, so I'm going to say anything past 90 degrees just duplicates options less than 90 degrees. So we only need to consider options for theta between 0 and 90. I included those in brackets. I think we understand it's not actually going to be at the endpoints, but we may as well include them. Okay, so that's our practical domain. All right, to find, or not to find. All right, so the max of L will be where L prime of theta is equal to 0. Oh, you know what? We can't use 0 or 90 here, and I'll tell you why. And in fact, we'll go here and just say So 0 degrees makes what? Sine of 0 is 0, makes 9 over sine theta undefined. 90 degrees makes 6 over cosine undefined. Okay, so that's why I took those out of brackets. We actually can't use 0 or 90, which is kind of interesting. Uh, by our definitions, our mathematical definition of L, uh, the perfectly vertical and the perfectly horizontal configuration are just not options for us. Um, which is a little interesting. So the max of L will be where L prime of theta is equal to 0. So, um, how do I want to do this derivative? What would be the best way to do this? Should we do this? We could do this as quotient rules. It's kind of overkill for quotient rules. I would rather do it as a chain rule. Um, before we find L prime of theta, let's rewrite L of theta. So L of theta is equal to 9 over sine theta plus 6 over cosine theta, right? 6 over cosine. I guess I could just look here. 6 over cosine. Yeah. Okay. So what we're going to do is we're going to rewrite this as 9 sine theta to the negative 1 plus 6 cosine theta to the negative 1. This lets us use chain rule rather than quotient rule. Rewrite that so it's legible. Quotient rule. You don't have to avoid quotient rule. It's just it expands things and it makes things really messy, and we just have to simplify it. And so chain rule, what's really nice about chain rule is your resultant derivative is usually fairly close to simplified, or it's definitely more simplified than if we had done the quotient rule. So let's go through. So now we can say, okay, L prime of theta is equal to negative 9 sine theta to the negative 2 times derivative of sine is cosine. I'm going to lower this down. There we go. And now we can do plus, negative 6, we'll just call it that for now, times cosine theta to the negative 2, right? We have to subtract 1 from that exponent. And then we can say, okay, we took the derivative of the negative 1 part, chain rule, derivative of cosine is negative sine. All right, so now we'll just simplify. This negative 2, that's a sine squared in the denominator. That negative 2 just forces it into the denominator. So this is going to be negative 9 cosine theta over sine squared theta. Here, we have a negative and a negative. Those are going to cancel out, so we're still going to have a plus. This 6 and this sine are in the numerator, negative 2, so this cosine's in the denominator. So we'll have 6 sine theta over cosine squared theta. Boom. Okay. So there we go. This is our simplified. So now we can set L prime of theta equal to 0. So we'll do 0, or we'll do it this way. We'll do -9 cosine theta over sine squared theta plus 6 sine theta over cosine squared theta. We'll say that equals 0. So now this is just some algebra. So we'll add 9 cosine theta over sine squared theta to both sides. So we'll do 6 sine theta over cosine squared theta equals 9 cosine theta over sine squared theta. So now what we can do, let's multiply this side by sine squared theta to cancel that out. So we'll multiply this side by sine squared theta. At the same time, we'll multiply this side by cosine squared theta, and that'll cancel out there. So we'll multiply this side by cosine squared theta. And so here, sine squared times 6 times sine, well, we have 3 sines being multiplied. So we get 6 sine cubed theta equals on this side a 9 times a cosine times 2 more cosines, a 9 cosine cubed theta. So I'm going to do a similar thing to the last step. I'm going to do 2 steps at once here. First of all, I'm going to divide this side by cosine cubed. So I'm going to divide this side by cosine cubed. Those will cancel out. At the same time, I'm going to divide this side by 6. So those cancel out. So I'm going to divide this side by 6. So over here, sine cubed theta over cosine cubed theta. We got all the thetas together. Over here, 9 over 6. Well, really quick, we'll make a note in case you don't remember. Sine theta over cosine theta equals tangent theta. So this side will turn into tangent cubed of theta equals, and on this side, 3 over 2 if we simplify the fraction. All right, we're getting close. On this side, we can take a cube root. Boop, boop. And now we have tangent of theta is equal to the cube root of 3/2, which is just some decimal. And now the step we take, so when you have a trig function and the variable you're trying to solve for is inside that trig function, you use the inverse trig function. So we'll do that, and that will cancel out the tangent there. That means we also have to do a tangent inverse on this side as well. So finally, we get theta is equal to the inverse tangent of the cube root of 3 over 2. Yeah, but there it is. So what we can do, and you kind of have no choice but to do this, we go to a calculator, make sure we are in degrees, and we'll do its inverse tangent, then it's the cube root of 3/2. 3/2, right? Yeah. Okay. to put this. Oh, I have to actually paste it into the Miro board. I just took the screenshot and sort of expected it to just show up. Okay, here we go. A little note over here, right? The cube root of something is the same thing as that thing raised to the 1/3 power. So that's why we have a 1/3 exponent right there. Cool. And so this tells us that an angle of 48.86 degrees will maximize the length of pipe that can fit down the hallway. Or fit, let's say, around the corner. And so we'll do L of 48.86 degrees, which we'll remember is 9 over sine plus 6 over cosine um 9 over sine plus 6 over cosine which is approximately 21.07 feet. The longest pipe that can fit around that corner is 21.07 feet. Interesting. Maybe this is interesting. If there was a third dimension to this, which in real life there is, right? So those hallways, let's say it's just in a really normal space, and so the ceiling is the same in both sections of the hallway. It's the exact same height. All we'd have to do is know that height, and we would do that height then divided by the angle. Well, it does get a little bit more complicated because you have to because those angles can only be measured against planes, right? And so because you're doing multiple dimensions, you can't measure that angle, a single angle for all three, like you can here, right? Where that single angle sort of defines its orientation in the 2 dimensions. But anyway, this sort of extrapolates out to a 3D version of the problem. Which I would probably be encountered in like a multivariable calculus class, potentially, or like right before. So yeah, just they simplified it down to 2 dimensions, but you don't have to, and it doesn't get that much more complicated. The same exact concepts and tools will allow you to tackle that problem as well. So there we go. Oh, let's put it. I like to put it in the answer box there. I don't know why. That just amuses me. Oh, why am I doing that? Let's do it here. So there we go. That's an optimization problem. Um, so we didn't actually run into we it didn't seem like we ran into infinite solutions in here, right? Um, and in fact, I think I might get rid of this whole practical domain section. Um, it's useful to talk about, but uh the reason we didn't run into infinite solutions, or the reason we could have, and we actually did run into infinite solutions, was because of that nature of angles. That whatever angle you choose from there, if you then rotate 360 degrees either direction, you're back to exactly your same starting position. And if all you care about is sort of inclination, like this pipe, then you can rotate 180 every 180 degrees you rotate, you're in the exact same position. And so you get all this repeated behavior over and over and over again. So, if 90 degrees solves something, then 450 degrees also solves it. Negative 270 degrees also solves it. Um, and so we should have run into infinite solutions. The reason we didn't is because of a limitation of the inverse trig function. Oops, come on. Yeah. So I guess I need to show you on the correct screen. So down here, where we took an inverse tangent function, um, inverse trig functions can't give you multiple answers. They can only give you one value. And us, as the people using them as a mathematical tool, it is up to us to understand that there are multiple solutions here because of that cyclical nature. Fortunately for us, we had already realized ahead of time that we needed something between 0 and 90, and that's exactly the solution this spit out. If it it's entirely possible, depending on what our number was and how we entered values into this, that it could have spit out something like negative uh 3 degrees or something like that. I think that might be equivalent to this, or negative um it could have spit out something that is mathematically equivalent in this situation, but that was outside our domain. And so it would have been up to us to then figure out, okay, how does tangent cycle? And it repeats. Tangent actually repeats every 180 degrees. Um, and so it would have been up to us to then add 180 degrees to, or subtract, or whatever, to adjust whatever answer this inverse trig function gave until we got within our actual domain. So look at all those of the infinite equivalent solutions, find the one that's inside our domain. But we didn't end up needing to do that. Um, so yeah, so we have this. Let me capture it and put it in. Put it. So this is a problem from a student I work with one-on-one. Um, so rather than link to these, because I know that student isn't watching, um, I'm just pasting what I did here in the notes for the stream. I'm just going to take that and put it in our in our one-on-one notes. Boom, link it all together, lock it up, grab it, copy it. Okay, cool. Oh no. Okay, hold on. Okay, there's that. But I actually heard back from the student about one of the problems from yesterday. It doesn't on number 2. Oh, okay. They just entered one of the values wrong. Um, Excellent, y'all. Any problem submissions? I don't see any. Okay. Well, let's get the website up and going for Tamara. Because, yeah, since that stream isn't going to happen, I'm going to need to. Okie dokie. Website is updated. So I think freaking headband, man. I do. Um, Sunday, we, assuming there are no other questions, I do want to make some notes about factoring polynomials. Uh, it's kind of an evergreen topic, and I've had uh, some of my one-on-one students asking about it. It's a topic that we're visiting recently. Um, and so one, it'll just be a good chance for me to sort of summarize my ideas around it, and potentially give myself some things to use elsewhere with students, but also because I know students are asking about it, I should talk about it. So we will do that. We'll go over. And my goal, I think, because it's been slow, I don't anticipating have a ton of questions to go over. I think I'll go ahead and just use the time I have to expand on it, not just do a quick like. And I say this as if somebody's watching, but nobody is. But if somebody were watching, and so if somebody had been watching, I think it would be clear my style is not quick tricks. My style is long explanations. But the long explanations are true. The tricks aren't true. Um. So anyway, I think we're close enough to the end. I'm going to sign off here. The schedule just wouldn't allow a stream tomorrow, so I will be back Sunday. But please submit your questions. If I see questions come in, um, especially right now, I won't be able to wait till Sunday. I mean, I'll kind of need to because of the scheduling of it all, but like I will probably message those people that submit questions, um, or something. So just to let them know. Um, but yeah, please submit questions, and I will go over them on Sunday. And if there aren't any questions, we will talk about uh, factoring polynomials and the various topics therein. Good stream. I hope you all have a good night, a good end of your week, and I will be back Sunday for the chill Sunday stream. Have a nice night, y'all.